Hi everyone! Today we are going to be talking about a bug found in SAP's LZC and LZH compression algorithms. So SAP's LZC and LZH compression algorithms are SAP's proprietary algorithms used in the open source database MaxDB that is used by all SAP software. We'll get into the specifics of these algorithms later, as well as the vulnerabilities that they cause, but when the files these compression algorithms have compressed are later decompressed by the corresponding decompression algorithms, the database is vulnerable to attacker-supplied commands. If you haven't heard of SAP before, SAP is a $26 billion company that sells business efficiency, finance, HR, and analytics software, among many other platforms. Here is the complete list of their products, but because of this bug in the foundational database, they are all vulnerable to attack. On their website, SAP has a list of customer testimonials listing hundreds of the more than 365,000 customers the company serves. Some of these include Hallmark. Could the hack have allowed us to change the lineup for this year's holiday movies? Or the Kellogg Company. Could we have finally found the secret ingredient in Frosted Flakes that makes Tony the Tiger say they're great? Probably not, but here's some of the other companies that could have had their software compromised. And remember, these are just the companies that want the world to know that they use SAP. SAP's website reports that 87% of Forbes Global 2000 companies are SAP customers, just showing how huge the number of companies that could be compromised by this vulnerability in the compression algorithm really is.
Before we get into the technicalities of this vulnerability, we first want to give a quick shout out to Mr. Martin Gallo from Core Security for dedicating his time and his effort into researching these multiple SAP protocols and products to provide you with this bug that we are going to talk about today.
So I'm Martin Gallo from the consulting team of Core Security.
Wow, what an introduction. Really makes you wonder if there's a correlation between the strength of your accent and the number of bugs you find. On a more serious note, it's actually extremely impressive because Mr. Gallo actually won the Pony Awards that year for the most sophisticated server-side attack. And what makes this topic super relevant to what we've been learning in class this semester is that this attack is actually just a buffer overflow. So, do you guys remember how we had to go through all those seemingly useless roadblocks that Emer put in the way in the homeworks? Like, it's Friday night, all your friends are out having fun without you, and you're just at home trying to figure out why overflow 2 needs 3 files of different lengths. Or maybe the next one where the ASCII sum of the values have to be divisible by 256 and contain rush key in the exploit. And then why you have to do it again. What about when you only have a 4-byte buffer? So if you thought that was hard, Martin Gallo will blow your mind with a real-world example showing how complex it can actually get and why these roadblocks exist. Coming up, we will show you what these vulnerable functions are in the MaxDB source code. But first, I will briefly cover the DIAG protocol, which is critical in understanding how SAP products communicate with each other and break each other. DIAG stands for Dynamic Information and Action Gateway. Basically, it's just a proprietary SAP protocol used for the communication between the SAP system backend and a diverse set of different SAP graphic user interfaces. So since it is a proprietary protocol, it's much more of a black box approach when you're trying to figure out how it actually works. So if we want to look at it, we have to tinker around with different applications and then intercept and examine the packets that are produced in order to craft exploits based on the different packets that we see. So this is kind of the opposite of trying to reverse engineer the binaries and kind of guess how the SAP system was written. So that being said, now you must wonder, what do these DIAG packets really look like? And basically, every packet starts with a network interface protocol header of 4 bytes. This is basically just done for some error checking in a different protocol. But then this is followed by an optional DP header that is only included with the first initialization packet of a communication. Next is a DIAG header, which basically acts as a flag to tell the system that we are using the DIAG protocol. This is followed by an optional compression header, which we will have to include if we are trying to reach the LZH or LZC vulnerabilities that we are here talking about today. And finally, we have the actual payload, which contains the body of the packet and all of the different files and information that the packet is trying to transmit. So Martin Gallo actually created his own Python library called pysap. The repository link is posted below, which specializes in crafting and sending these packets to different proprietary SAP protocols such as DIAG. So you can actually use this tool for other protocols such as RFC. But this next demo is just going to quickly show what it looks like, what a DIAG packet looks like when we're using his tool.
This is how a packet looks using these capitals. So obviously, each of these items and each of these fields can be manipulated, and you can also craft your own packets using this tool.
The first way that SAP decompresses archive files is using the LZC decompression algorithm. This vulnerability is a stack-based buffer overflow vulnerability that allows an attacker to inject machine code onto the stack and either execute it or cause the program to crash in a denial of service attack. Code is injected into the decompression algorithms using an archive file, which is then decompressed and allows the code to execute. We'll go into more specifics about this later. The vulnerable code in question is right here. It's a little difficult to understand since the code involves so many macros, but as an overview, the information in this variable code is attacker supplied through the output of the archive file payload. The stack will overflow if code is greater than 256, and the value in the prefix table, that's this line here, is also greater than 256. It's then possible to fill in the stack with machine code by controlling the values stored in the prefix and suffix tables. However, the biggest issue is here. You will see that this macro overflow check is used as a catch-all for buffer overflow errors. If we scroll up to line 65 that has the macro itself, it looks like the programmer that created this code thought this would catch all possible issues, but in fact, this macro, CS stack check, is not enabled at the time of compiling. If def, right here, allows a section of a program to be compiled only if the macro that is specified as a parameter has been defined, no matter what its value is. So, while this isn't defined, we skipped over to the else statement, where we're defining overflow check as essentially an empty macro, as opposed to the macro it is here, where it's actually checking to see if the stack is being overflowed. Therefore, the overflow check macro isn't catching anything, and the attacker may inject harmful machine code into the program.
The second way that SAP decompresses archive files is known as the LZH decompression algorithm. We were also able to obtain the source code of this header file and identify exactly where and how it can be manipulated for evil. So right about here is where things start going a little bad when we try to set up a new table entry. And basically what we have here is a set of if-else statements where on line 340 in the final else block, we see that the arrays E and D are both indexed by P minus S, which is actually an attacker-controlled value. So the problem with that is that if we were able to sneak in a very large value for P, then we would end up crashing the program and resulting in a out-of-bounds read access, which when used for bad purposes could lead to things such as distributed denial of service attacks, DDoS, for example. So yeah, definitely want to make sure you ask for permission first, though, before you do something like that, guys. Now that we see where the code actually breaks, how do we exploit the LZC or LZH compression vulnerabilities to actually alter the flow of the program? Well, for those of you who have taken systems programming, you probably know about myAR and what an archive file is. So an SAR file is basically just SAP's version of an archive file. For those of you who don't know what an archive file is, it is basically just a single file that aggregates the metadata and contents of multiple different files to make it easier for portability and storage purposes. So if we are able to trick the DIAG protocol into decompressing one of these files, then we can reach that buffer overflow vulnerability. Without further ado, here is the man, the myth, the legend.
First, I will start a netcat here. Sorry. I will launch an exploit for the vulnerability that I found. So here you have a reverse shell with SAP service account, which is the account that runs all the database services and all the SAP services.
As we've said before, these vulnerabilities affect a large range of products. The LZH vulnerability only allows an out-of-bounds read, so the only attack that can occur is a distributed denial of service attack, or a DDoS attack. But the LZC vulnerability can do much more. According to Martin Gallo, it can do attacks against server-side components. SAP NetWeaver is an application server that runs the compression algorithms along with MaxDB. Components of NetWeaver handle compressed requests coming from the different clients connecting to them. A remote, unauthenticated attacker might be able to connect to the NetWeaver services and trigger the vulnerabilities by sending specially crafted packets. It can also do client-side attacks. An attacker might be able to perform client-side attacks against users of the affected programs that handle compressed data. For instance, an attacker might send an especially crafted CAR or SAR archive file aimed at being decompressed using the SAP CAR tool, or create a malicious SAP server and convince users to connect to this malicious server using SAP Graphic User Interface. It can also perform man-in-the-middle attacks. Most of the services affected by these issues are not encrypted by default, so an attacker might be able to perform a man-in-the-middle attack on the communication between two parties and trigger the vulnerabilities by injecting malicious packets into the communication. So we've told you about all the issues in this code, but how do we make sure it doesn't happen again in the future? The vulnerability in the LZH algorithm that Derek talked about is very avoidable. By utilizing a check for an out-of-bounds number in S, this vulnerability would be completely avoidable. Programmers should always make sure that they're checking for out-of-bounds numbers so this doesn't happen. Programmers should also put up defenses against attempted machine code injections, so that vulnerabilities like the one in the LZC algorithm are more difficult to do. Any input payload should be examined to make sure it contains the expected information before it is decompressed. But in conclusion, always remember to check your code for exploitable security vulnerabilities before using it in the foundational platform for a multi-billion-dollar company. Otherwise, you may need to talk to Martin Gallo. Thanks for listening.